All right, under standard conditions, a temperature, what was the temperature? 1650? Well, anyway, the temperature was very high. That was required to get this to become spontaneous. And so then we tried to do it at room temperature under non-standard conditions. RT under non-standard conditions. But, you know, the pressure came out some ridiculous pressure. The pressure was too low to achieve. And so we tried a combination, and we didn't finish this quite. The calculation was set up for this. And so what is a pressure that we can achieve without too much difficulty? And so if we look at our vacuum pumps, we probably can achieve like a half an atmosphere without too much difficulty, or half a bar. And so 3 was a combination, right, of temperature and pressure. In this case, the pressure would be the non-standard, since concentration doesn't play into this. And so a pressure that we could achieve was something like 0.5 bar without too much trouble. And so at this pressure, which is a lower pressure, about half the pressure, what's the temperature going to be? And so we solve our equations, you know, for temperature. And the equation for temperature comes out as delta H naught over, what is it? Delta S naught minus R ln Q. Yeah. Could you derive this equation? You'd either have to memorize it or derive it. So it's good to be able to derive it. Well, anyway, we can go ahead and plug this in. We have our delta H. What was the delta H value again? From your notes from yesterday? 157.3 kilojoules. Delta S?
93.07 joules per Kelvin.
R? 8.3145 joules per Kelvin. This is just going to be for mole of CuO. ln of Q. Now Q is our pressure in this case. It's 0.5 to the 1/2, right? Because that's what we got earlier. 0.5 to the 1/2. And so what is the temperature? Well, you know, having a lower pressure means we don't have to go as high in temperature. And so since we don't have to go as high in temperature, it might be more feasible because the earlier temperature was so high. It's like 1650. Let's see what this temperature comes out to. So can somebody calculate the temperature that we get from this? A combination of non-standard conditions and a temperature not equal to 298. So a combination of temperature change and non-standard conditions. So the strategy here is we'll try it under standard conditions and just change the temperature. Well, that failed. Well, it didn't really fail. It just, the temperature was so high. So then we tried it at a room temperature, but just tried to go non-standard conditions. That is, alter Q, but keep it at 298 Kelvin. Well, that was both of these are difficult because this is temperature was too high. The pressure here is too low. We don't have any vacuum pump. Did I show you the ultra high vacuum stuff? Yeah, we don't have any of that. And even if we did have that, we'd be orders and orders of magnitude too far. So it wouldn't work. To achieve that pressure, even if we brought it out in space, it'd be very difficult to achieve that pressure. And so, rather than that, we might try something like this. You know, a combination of temperature and pressure. There are devices that work like this. One device is called the vacuum oven. Have you ever heard of a vacuum oven? Did I talk about that? Hmm?
Pressure cooker?
No, not a pressure cooker. A vacuum oven. Ever tell you about a vacuum oven? A vacuum oven is a box like this, and then either the box it's a pretty heavy-duty oven with a big door, and it's a glass door like this, very secure. So you take your stuff and you put it into the vacuum oven. And what the vacuum oven is good at is it's good at drying stuff. It's really good at drying stuff because normally when you dry something, you have to heat it to over 100 degrees C to drive off the water, you know, minimum 100. Our drying ovens, do you know what we set those to? Like 112, 120 degrees C. Right? But let's say, oh shoot, my book got wet. My book got wet. Do you want to cook it in the oven at 112, 120 degrees C? No, because what's going to happen is it's going to start to char the paper, and the paper is going to start to turn brown. So if your book got wet, soaking wet, what I do is I just throw it in the vacuum oven. You throw your book in the vacuum oven, you know, and you close the door, you turn on the pump. The pump starts sucking air out of here. And then you only have to turn this up to like 30, 40 degrees C. You turn it up to 40 degrees C, is that enough to char your paper? No. And so your book is going to come out nice and dry, and the paper is not going to age at all. It's not going to be oxidized. Well, this is very important for a lot of organics. When your organic compounds get wet, a lot of them are combustible. A lot of them are highly flammable. And so to cook them is kind of, well, two things can happen. One, you're just going to prematurely age them or decompose them. Or two, you know, they can catch on fire. And so what you want to do is you want to dry them at very low temperature. And this is how you can dry them at low temperature. In fact, we can dry them at room temperature. Just turn on the vacuum. And dry quickly at room temperature. So this is number 3. We're trying a combination of things. You know, this way, you know, we don't have to go as high a temperature as number 1, and we don't have to go to as low a pressure as number 2. We're going to meet somewhere in between the two. You know, and so let's see where that somewhere in between is. So what did the temperature come out to? Did somebody calculate it? So 0.5 ln times 8.3145 minus 93.07. $1,639 Kelvin. So it was like, I think it was like 1650 to 1639. Did having a half a bar vacuum really help? Barely. You know, the temperature is a little bit lower, but it's not by much, right? And so, in other words, you know, any way you do this, it's going to be expensive. You know, vacuum equipment's expensive. High temperature is expensive. You know? And so, is there a cheaper way of doing it? And it turns out there's a much cheaper way of doing this. This is option number 4. Option number 4 is trying to do coupled reactions. Well, coupled reactions is nothing new. we've already done a couple of reactions. Let me just tell you. The one we just did not so long ago. The coupled reaction was this. If we look at silver chloride solid, is it very soluble? Silver chloride. Silver chloride's not soluble. That tells us that the delta G under standard conditions here is greater than 0. Actually, this delta G value we can calculate easily using appendix D data. So rather than just saying this is non-spontaneous, silver chloride doesn't spontaneously dissolve in water, let's go ahead and calculate what that number is using the data. From appendix D, since I don't have it up, I have it here. So let me bring up appendix D. All right, so we want delta G. The easiest way to get delta G is delta G's of formation. So we look, here's delta G of formation of silver ions. So this is the product, silver ions, 7711. Then we need the delta G of formation of chloride ions, which is on a different page. So we got 7711, the products minus the reactants. And so let me write that over here. So under standard conditions, silver ions 7711 kilojoules per mole. We have 1 mole of silver ions. Minus the reactant is going to be a minus 109.8. So a minus 109.8 kilojoules. So null of that. And then we need the delta G of formation of chloride. Let's look for delta G of formation of chloride. Delta G of formation of chloride is minus 131.2. This is a plus of minus 131.2 kilojoules. And so what does this come out to? So I got 7711. Oops. 7711 minus 131.2. Plus 109.8. Oh boy. I screwed that up. Does somebody have it? 55.71. So it's fairly non-spontaneous, 55.71. And so since I have that under the board, we'll just rewrite it over here. So silver chloride solid goes to silver ions plus chloride ions, delta G naught 55.71. But what's one way of getting silver chloride to dissolve? We just use Le Chatelet's principle. And how can we do that? How did you dissolve silver chloride in the lab? We attacked the chloride or the silver ions? Silver ion with what? With ammonia. and we form the diamine. Silver ion. Well, what is delta G for this? Well, when I go in here, let's take a look over here. Do I see diamine silver? Do I have the data from appendix D for diamine silver? No, I don't have the data for diamine silver ion. It's not in any other tables. So am I stuck here? I don't have the delta, I can't do the delta H, I can't do the delta G, the formation for this. Am I stuck, or is there another way to determine delta G naught? Is there another way I can get it without using appendix D data? The answer is yeah. You know, what else does delta G naught equal? It equals minus RT ln of K. Well, do I have K for this? These are all aqueous solutions. And so KEQ is equal to KC. And Kc equals, this is a special K. What is this K called? This is called KF. Do you remember KF? KF, we got KF. We have KF in appendix D. So I'm not this table, but I can use the other table. 1.6 times 10 to the 7. 1.6 times 10 to the 7. So this is going to be minus R, minus 8.3145. T is 298 Kelvin. This is joules per Kelvin. 298 Kelvin times ln of 1.6 times 10 to the 7. And so let's calculate that quick. 1.6 times 10 to the 7, take the natural log of that, times 298, times 8.3145 equals this. The units of delta G are typically in kilojoules, so I'm going to convert this to kilojoules. I'm not going to show the conversion, but it's going to be 46.80 kilojoules negative. $46.8, is that right? Yes, that is right. So when I add these two together, what do I get? Is that what you got?
What, 41.1 kilojoules?
41.1? 41.1, even worse. What's that?
What, negative?
Negative 41.1? Let me just redo that, thanks. So this, yeah, 41.1 kilojoules. I was hoping it would come out more negative. This one doesn't work the best. 41.1 kilojoules negative. Was this right? Yeah, okay. Just want to make sure. So that's 55.71 minus 41.1. Because if I add these two equations up, I'll get silver chloride solid plus 2 ammonias. This is going to go to the diamine complex plus chloride. Delta G for this net is like Hess's law. When we add the reactions, we just add up the delta G's or the delta H's. Delta G is an energy term. Energy terms are extensive like this. And so when we add it up, I come up with 14.61 kilojoules. Well, this still says what? Plus 14.61 still says non-spontaneous. But if you have a 14.61 compared to a 55.71, there's a pretty big difference between those two, right? In fact, this is getting closer to all reactants, but this is getting closer to a mix, a significant mix of reactants and products. So in other words, by coupling this, it becomes much more soluble than before. Does that make sense? And so this is another way we could do these reactions. So all we have to do is we have to couple this reaction, the reaction that we want, with something. And so we have to think about what we can couple it with. And this is just kind of Le Chatelier's principle in action. So we got copper 2 oxide solid, and we want it to go to copper solid plus O2 gas. We want to keep the copper, right? And in fact, the whole purpose of this is to recover the copper metal. And so we don't want to lose the copper metal. And so what we need to think of is we need to think of something that attacks oxygen. And so I'm going to think about my chemical properties of oxygen. What are the chemical properties of oxygen? It's an oxidizer, right? It wants to oxidize something. It wants to oxidize a flammable or combustible material. And so what we can do is we can use a combustible material to couple this with. And so we got to think of what's a cheap. You know, we don't want to use expensive combustible materials. We want to use something cheap. What is cheap? Methane? Methane's cheap, that's true, but there's something even cheaper than methane. You know, people heat their homes with methane, or they could heat it with something even less expensive, but probably doesn't burn nearly as clean as methane, and they just dig it out of the ground. Coal. Coal is cheap, and coal's made up primarily of carbon. And so if you take some coal, right, and then burn it with the oxygen that's produced from this, what will you form? Well, coal doesn't burn so cleanly, and in this case, the coal is going to burn to carbon monoxide gas. It just doesn't burn that clean. But nonetheless, this is a combustion reaction, and combustion reactions are favorable. So over here, the delta G wasn't so favorable. Delta G naught was, what was it, plus 157 kilojoules. And so let's see what this is here. And so we can do this really quick. We can figure out the delta G for this using appendix D data, or we can just have it given to us. Well, let's just do the additional practice. We're going to figure out what it is. Because it's so simple, this calculation. Delta G of formation for 1 mole of carbon monoxide is minus 137.2. So what we do is, in order to find out delta G for this reaction, we do the delta G of formation of the products minus the reactants. Delta G naught for this would be delta G of the products. Well, the product is minus 137.2 kilojoules. We're forming a mole of that. Minus the reactants. What's the delta G of formation of carbon? 0. In graphitic form. What's the delta G of formation of oxygen? O2. It's also 0. It's the same reason why the delta H's of formation are 0. And so this would be 0 plus 1/2 times 0 equals 0. So this is it. So that was a simple calculation. Now let's add up these two and see what we get. Was it 157? Huh? 157.3. So if we add up these two, it's still not quite there. Shoot. You know, we don't get oxygen as a product. In this case, we're going to get carbon monoxide. But nonetheless, we get our desired product is copper. But unfortunately, it's going to be more spontaneous, but not quite as spontaneous as we'd like it, you know? And so what does it come out to, the delta G net for this one? The delta G for this one is going to come out to 157.3. Minus 137.2. 20.1. Hey, that's a lot better, isn't that? And so we should be able to produce some copper, but it isn't quite spontaneous. We want a delta G less than 0, right? Well, let's see what they did here. Did I read that wrong? Let me just see. They got a minus 175 for the formation of carbon monoxide. Let me see if I read that wrong. I didn't read that wrong. I have a formation 137. Why is their formation different than mine? The delta G for what? Oh, 129.7? This one? Oh, this one here.
Yes.
Oh, 129.7? Was that what we calculated last time? All right. This is wrong. But why is there carbon monoxide off from mine? Somebody tell me why? Why is there delta G for carbon monoxide this different than mine? Look at it, look at the slide and tell me. You can figure it out. Hmm? I'm sorry? Oh, no, not the first. The first one's definitely going to be different than mine. First one's definitely different than mine. I'm talking about this second one here. Why is this second one different than mine? They got 175. I got 137.2. Why is it so different?
Didn't we just form copper oxide and they formed?
Well, I'm just worried about this second reaction here. It's the temperature. Their temperature is 673. My temperature is not. There's no such thing as standard temperature, but it's 298. And so the temperature is different. If I did this reaction at a different temperature, then delta G is going to be different. Let's see. How can I calculate that delta G value? Well, let's just confirm that. I want to confirm the minus 175 because it's at a different temperature. So let's take a look and see the numbers there, actually. So in order to see how delta G varies with temperature, we need to know delta H and delta S. So delta G naught is equal to delta H naught minus T delta S naught. And what we're going to do is we want delta G at 673. Was it 673 Kelvin? But we're going to use delta H naught at 298 Kelvin, and we're going to use delta S naught at 298 Kelvin, hoping those don't that different, and keep the temperature at 673 Kelvin. So delta H naught, since this is such an easy calculation, I'm going to go ahead and do it because this is what we call a formation reaction. This is a formation of 1 mole of substance from the elements in their standard state. And so I just read it off the table. I don't have to do any calculation. And so delta H of formation of carbon monoxide is minus 110.5. And so this is easy, minus 110.5 kilojoules. Delta S naught, now that isn't easy because delta S naught is different because, you know, in a formation, the elements are always 0. But when we're looking at the entropy, these are not going to have 0 entropy. And so the entropy is a bit of a pain because I actually have to calculate that. So I'm going to look at the entropy of the product, carbon monoxide. The entropy of the product, carbon monoxide, is 197.7. And so that's the product, 197.7 joules per Kelvin, minus the reactants. And then I got to look at the entropy of carbon, solid, and the entropy of oxygen. And so going back here, carbon solid has an entropy, actually I don't have to walk over the computer, let's look at it here. Carbon solid. Now, what are we looking at? Is coal made out of diamonds or mostly graphite? Coal's mostly graphitic carbon and amorphous carbon. Amorphous carbon is going to have a higher entropy than, because you know what amorphous means? Amorphous means structureless. And so it isn't a well-ordered crystalline solid. And so we don't have the perfect one, but we'll just go ahead and use 574 for the entropy here. So that's 5.74 for the carbon, and then we have a half a mole of O2, so this is joules per Kelvin. So that's plus 1/2 the entropy of a full mole of O2. So what is the entropy of a full mole? Well, the entropy of a full mole, as I remember, is 205.1. Is it? Well, I don't know. To 5.1. So that's going to be 1/2 times 205.1 joules per Kelvin, because we have a half a mole. And so let's see what it comes out to here. So let's do the 205.1 divided by 2 first, plus 574. Oh shoot, this calculator is something. This thing. Oh, this calculator is much better. Okay, the entropy is 89.41. Minus 673 Kelvin times 89.41 joules per Kelvin, and then we got to convert it into kilojoules. And so a kilojoule is 1,000 joules. And so let's see what this comes out to. Times 673 divided by 1,000. Minus 110.5. So I get a delta G naught equal to minus 170.6 kilojoules, minus 170.6, at 673 Kelvin. Their delta G is still different than mine, but it's closer. You know, I got about 171, they got 175. So this delta G could have come from other data, you know, actual measurements. But we calculated based on Appendix D. So at going back to this, this one here, it's too bad. I wanted this one not to work out right, but it's okay, it worked out. This one here is 129.7 minus 137.2. That equals minus 7.5. And so this becomes spontaneous. What can you make how can you make this more spontaneous at room temperature? You can make it more spontaneous at room temperature by using a better fuel. Right now we're using coal. This is generating minus 137.2. But what if we use something like hydrogen gas? You know, if we use something like hydrogen gas, although hydrogen would be dangerous, we could see what difference that would make. Because instead of forming carbon monoxide, if we use hydrogen gas, we'd form H2O liquid. Delta G of formation for that would be minus 237.1. And so, let me erase this. If instead we use a more powerful reducer like hydrogen, to form H2O liquid, then we're looking at a delta G naught of minus 237.1 kilojoules, which is going to make the overall delta G naught, and this is going to give us CuO solid plus H2 gas goes to copper solid plus H2O liquid. And so the product is even better. Rather than forming carbon monoxide, we're going to form water. And this is going to be much more spontaneous because this is going to give us an overall delta G of 129.7 minus 237.1, which equals minus 107.4. So minus 107.4 kilojoules versus minus 7.5 kilojoules. And so we could pick different reducing agents to see, but this is how we can make a non-spontaneous reaction spontaneous at room temperature without having to resort to extreme. You know, just as long as the fuel cost is not too high, it works out okay. A lot of biological systems do this. In fact, when we look at a lot of biological reactions, they show them differently. They show them like this. These are all coupled reactions. And so we're going along this way, and they couple it with this reaction. This is coupled with this reaction. Sometimes it splits in. This is just reactant. This would be another coupled reaction here, etc. And so they have this thing. This is called the citric acid cycle, or the Krebs cycle. And so in metallurgy and in biological reactions, we see this a lot. All right, that pretty much concludes chapter 19. You know, just different ways of trying to make the reaction more spontaneous and then relating to the thermodynamic variables of different things. We're going to move on to chapter 20 next, which is electrochem. Look. Yeah. We have the contents. Electrochem deals with redox reactions. So let's just take a look at the redox. Concepts. Again. Okay, we have two redox reactions happening here. This one, we have a chunk of copper solid. And this is a solution of copper 2+ here. And actually, not that. It is now a solution of copper 2+, but it's copper solid reacting with silver ions, 2 silver ions here. And when copper solid reacts with 2 silver ions, we're going to produce copper 2+ plus 2 silver solids. And so what we have is we have the reducing agent, copper. We have the oxidizing agent, silver ions, going to copper 2, which is the oxidizing agent on the product, and silver, which is the reducing agent on the product side. And when we compare copper versus silver, copper is a better reducer than silver. In Chem 4 and Chem 1A, we call it activity. You know, copper is more active than silver, meaning it's a better reducing agent. And so in Chem 4 and Chem 1A, activity is the strength of the reducing agent. And so it's going from stronger reducing agent to weaker. In other words, it's going from a more active reducing agent, or a more active element, in this case copper, to a less active element, silver. Silver's less reactive than copper. Likewise, it's going from a stronger oxidizer, silver ions, to a weaker oxidizer, copper 2. And so this is it. What happens is the copper, the strip of copper gets corroded. As it gets corroded, it forms blue copper 2 ions in solution. So we see the blue copper 2 ions forming here. And it's going to precipitate out silver. Silver precipitates out as needles. And we have very small needles here. Very small crystals of silver appear black in color. As the crystals grow bigger, then they have the characteristic silver color associated with them. But you can see the long needles here forming the fuzz. Over here we have the copper strip, but we're trying a different oxidizer. In this case, we're trying the oxidizer Zn2+. Zn2+ is too weak of an oxidizer to oxidize copper to copper 2 and reduce zinc to Zn solid. And it's too weak, and therefore there's no reaction here, Nr. In other words, we're going from a weaker reducer, that is copper, to a stronger reducer, that is zinc. That is, we're going from a less active metal, copper, to a more active metal, zinc. And then we're going from a weaker oxidizer to a stronger oxidizer. And so this is what we've done already at the beginning of the semester, and this is what you've already done in Chem 1A and Chem 4. And so what we're going to do in this chapter is just more redox, except we're going to do things a little bit differently in this chapter here. One of the things that we're going to do differently is we're going to look at this reaction here in more detail. In this reaction, we can separate it into 2 half reactions. There's copper solid going to copper 2+, and the process is going to generate 2 electrons. Those 2 electrons are going to be consumed by 2 silver ions. And so the 2 silver ions picks up the 2 electrons and then forms 2 silver solids. Okay, the first reaction here is what we call an oxidation half reaction. In the oxidation half reaction, we have the reducing agent, copper. In the second half reaction here, this is called the reduction half reaction. And in the reduction half reaction, we have the oxidizing agent, silver ions. And so the oxidizing agent, silver ions, are reduced to silver metal. That process is called reduction. The reducing agent, copper, is oxidized to copper 2+. This process is called oxidation. And so sometimes people get it mixed up, but one way to keep these in track is oil rig. Have you heard of oil rig? Oxidation is loss of electrons. So this is oxidation, is loss of electrons. Reduction is gain of electrons, oil rig. And the other way of remembering this is the agents. Oxidizing agents, what do they? Oxidizing agents are electron poor or electron rich. Oxidizing agents are electron poor. Oxidizing agents want electrons. They're out to oxidize something. Okay. Reducing agents are electron rich. Reducing agents are out to reduce something. They're going to reduce something. And so oxidizing agents cause oxidation to occur. Reducing agents cause reduction to occur. But, so what we have here is we have direct transfer of electrons. The silver ions attack the copper and take the electrons away. The silver ions are electron poor. Copper is electron rich, I guess, and the silver ions will take the electron from the copper. Well, silver ion can't oxidize everything. So here we see the net reactions here. What we're going to do is this. We're going to set up something like this, in which we're going to transfer the electrons. You know, the copper is the electron rich. The silver ions are electron poor. And what we're going to do is we're going to have the silver ions take the electrons from copper, but in the process of taking the electrons, it's going to pull the electrons through what we call an external circuit or external wire over the silver over here. And so we can use a redox reaction like this to generate electricity. Electricity is a flow of electrons. And so the way we're going to do that is we're going to have silver ions over here. And we have nitrate, because this is silver nitrate. The nitrates are spectators. But that seems odd, because what's a better oxidizer? Are silver ions a better oxidizer or nitrate ions? Well, I know the best oxidizer on the chart. What is the best oxidizer on the chart? The best oxidizer on a chart is fluorine. And so we go down, and the first species we hit is nitrate. Where's silver ions? Well, silver ions are actually below that. Here's silver ions. Silver ions are a weaker oxidizer than nitrate. So if anything's going to be pulling for electrons, you know, because the oxidizer is electron poor, it wants electrons. So what's going to be more electron poor, the silver ions or the nitrate? And it looks like the nitrate ions are more electron poor because those are more powerful oxidizer. And so shouldn't it be the nitrates trying to take the electrons rather than the silver ions? And the answer is yes, but there's one key ingredient missing. And that is not water. We have plenty of water. Is H+. We don't have any H+. Let's say you're trying to make some cookies and it requires 1 cup of sugar and 4 cups of flour. And you say, well, I don't have the flour, but I'm going to go ahead and make the cookies anyway. Is that going to work? No, it's not going to work. We're not going to get these products. And so what's going to happen is, since we don't have the nitrate, it's not going to react in the same way. In fact, it's going to be non-standard conditions. We need 1 molar nitrate there. And so what we say here is missing nitrate. Not nitrate, it's missing H+. Sorry, there's nitrate here. It's missing H+. Therefore, it's a spectator. Well, there's isn't there a tiny bit of H+ in water? Yeah, it's really tiny. It's 10 to the minus 7 molar. And so, you know, we could calculate the potential. In other words, we could calculate the driving force for this, but the driving force is going to go way down because the concentration goes way down. And what does Le Chatelier's principle says? You know, if this concentration shrinks all the way down from 1 molar down to 10 to the minus 7 molar, that's a huge drop, right? and it's going to favor shifting it to the left. So this doesn't behave quite the same. Now, if we add acid in here, then it's a different story. If we add acid in here, then silver ions and oxidize, or nitrates and oxidize. Nitrate's going to be better because there's acid present. But there's no acid present. And so what is the silver ion going to want to do? It's going to want to take electrons. Well, it's going to want to take electrons from anything it can. Well, metals are electron rich. And so let's try to take electrons from metal. But this is very tricky, because the metal I'm going to put in this beaker is not copper. If the metal I put in this beaker is copper, then the silver ions can take the electrons straight away from the copper. Instead, I'm going to put silver. If I put a slab of silver metal in here, are silver ions going to be able to take electrons from silver metal? No, it's going to be a tug of war, it's going to be a tie. Right? And so you got silver on this side, silver on the other side, they're pulling for the same electron, it's going to be a tie, basically, because both of them will end up with a plus charge. And so anyway, so silver's not going to be successful, but you know what metals are? Metals, they call it a sea of electrons. Have you heard that term, sea of electrons? They're a sea of electrons because they got a lot of electrons here. And these electrons, let's say these silver ions try to pull these electrons, they aren't going to be successful. But as they try to pull these electrons, then the sea gets a ripple in it. And that ripple is felt through because it's pulling the electrons, and that ripple is going to be felt until we hit this wire. Now, we're going to have a piece of copper wire attached here, and as long as the copper wire is attached to the silver cleanly, there isn't any corrosion here or anything to cause what we call electrical resistance, you know, it's got a clean contact, then the sea of electrons is going to extend into the copper wire itself. You know, the two seas are connected, like a little sea with a big sea, or ocean. And so this ripple is going to be felt all the way to copper. Well, silver ions, are they strong enough to oxidize copper? Yes. Silver ions are strong enough to oxidize copper. But the problem is, if they oxidize the copper here, what do we form? We form copper 2 plus in air. Are copper 2 ions stable in air? They aren't stable in air. Copper 2 ions are stable in water because of hydration. You know, hydration or solvation, this is why lithium is the most powerful reducer on the chart, is because of the hydration energy or the solvation energy of lithium ion. You know, it's fairly stable. And so this is too unstable. Oops, this is supposed to be a different color, but that's unstable. And so this copper wire is going to extend all the way over, and it's going to be connected to a chunk of copper here, or a strip of copper, and we'll have a clean contact here. And so this ripple in the sea of electrons is going to be felt all the way over to the other beaker, because all these electrons are forming a chain like this. Now, as soon as it hits a copper atom that's submerged underwater, then this is what can happen. So that ripple is being felt all the way down to here. Well, this copper atom has 2 electrons. Those 2 electrons get pulled off. So the 2 electrons get pulled off and fed into here, and what gets spit out is a copper 2 plus AQ. Well, copper 2 plus AQ is a heck of a lot more stable than copper 2 plus in air. And so now what we've done is we've oxidized our copper. But the copper was way over here in the left beaker, not in the right beaker. But we took advantage of the properties of metals such that we could oxidize it remotely. And what's going to happen here are the electrons are going to flow this way. The electrons will flow left to right. And then these silver ions will pick up the electrons here, and then they're going to deposit silver atoms here and here. And then we're going to grow little needle-like crystals coming off the face. And so this silver plate here is going to start growing a fuzz on that, corresponding to crystals of silver, whereas the copper here is going to start to become corroded and eaten away as we start to oxidize the copper into copper 2 ions. And so over here we have copper solid going to copper 2 plus 2 electrons. Those 2 electrons are fed through what we call the external circuit and go to this other metal plate where they come into contact with the 2 silver ions. And the 2 silver ions will pick up the 2 electrons to form 2 silver solids. And so what we've done here is we've just generated electricity. Again, electricity is this flow of electrons. But the electricity isn't going to last very long because there's going to be something that's going to stop the electrical flow immediately. What's going to stop the electrical flow immediately is this. As we generate the copper 2 ions here, we get positive charge buildup here. And so as the positive charge builds here, the same thing over in this beaker. We're going to consume the ions here, and then they're going to plate out as silver atoms. And so we're losing the cations, but the anions are still there. These are spectators. They aren't doing anything. And so what's happening in this beaker over here is the negative charge builds. You can't sustain this for very long because when you have separation of charge, it creates a voltage, like static electricity. And this voltage grows extremely high with a minute amount of ions or minute amount of charge generated. And so what happens here is this is going to stop the electricity from flowing. In other words, it's going to stop the electrons from flowing. And so what we have here is we have a problem. And the problem is space charge. That is, it's a problem of electrical neutrality. Even though the whole thing is electrically neutral, we can't pack all the positive charge in one beaker and all the negative charge in the other beaker. We generate an enormous voltage, and it would create a lightning bolt of electricity going through to neutralize that space charge. And so the solution to this is the salt bridge. The salt bridge will fix this problem. And the salt bridge, what that is it's just a tube filled with some salt solution. In this case, we have potassium nitrate solution. And so as the copper 2 ions are being generated here, for each copper 2 ions, 2 nitrate ions will migrate from our potassium nitrate solution here. And there's some disc here to prevent it from diffusing out immediately. And for every 2 silvers consumed, 2 potassiums will go in here. So the salt bridge maintains electrical neutrality because 2 nitrates flow this way, 2 potassiums flow that way, so it's neutral. And then these 2 nitrates will help balance the charge of the copper 2s, and these 2 potassiums will help balance the charges of the nitrates here. And so that's the salt bridge, and once we have the salt bridge in there, then the electrons will start to flow and will generate electricity. Here. All right, so again, the oxidizer here is trying to pull the electrons, and eventually it's going to be able to pull the electrons off the copper way over there. Let's take a look at another setup here. Looking at this setup here, over here in this beaker, we have copper 2 ions. And the copper 2 ions, which is giving it the blue color here, is trying to pull the electrons off copper metal. Is it going to be successful? No. But we see that that copper metal is connected way over here to zinc. Is copper 2 strong enough to oxidize zinc? It sure is. Copper 2 is plenty strong enough to oxidize zinc. So what's going to happen is it's going to pull the electrons off zinc, and the zinc is going to get oxidized and form Zn2+ in solution. Over here, the copper 2 is going to plate on this electrode. And so the net reaction here is the zinc is oxidized with copper 2 to produce Zn2+ and copper metal. The copper metal is going to grow. So this electrode is going to grow heavier. This electrode is going to shrink due to being corroded away. All right. We can attach something called a voltmeter here in the wire. What a voltmeter does is it essentially just measures the pressure on the electrons flowing through the circuit. And so let's say if you want to measure water pressure, you have a garden hose. You want to measure the water pressure, what you do is you just maybe block off the water with your palm and then just feel how much pressure there is, right?
But if water's leaking out, you know, you didn't create a very good seal. Water, are you measuring the full pressure? No. Or if you put it over your fingers and water's squirting out there, you really have to block it off, the flow, to measure the full pressure. Well, that's what a voltmeter does. If you put a voltmeter here, it's going to prevent the flow. And it's just going to measure the force or the pressure on the electrons. Well, that pressure is being generated by the silver ions. The silver ions are trying to pull the electrons through the circuit, right? And so we're going to measure that. Boom. And then we can assign a number to that. In this case, it's going to be 0.460 volts. That's the voltage there. Oops. Over here, this is a different story. In this case, this is a bigger mismatch. Here, we're going to have copper 2 pulling the electrons from zinc. The copper 2 is going to be able to pull these a lot easier. And it's not just pulling, but there's going to be resistance. Zinc is going to resist this. And so what we're measuring here is the net, or the combined effect. You know, zinc resisting the loss of electrons, and then copper 2 pulling the electrons off. Because zinc's ionization energy is greater than 0. You know, it's got a positive ionization energy, which means it requires energy to ionize. But anyway, the voltage here is 1.103 volts. And so what we're going to do is we're going to talk about the details of this cell. And so I'm going to complete. That drawing up there is not totally complete. So let's complete this here. And so over here, what do I have? Over here I have my oxidizer, copper 2+. And so this is my oxidizing agent. And the oxidizing agent is trying to take electrons. It's going to take electrons from my reducing agent. My reducing agent here is Zn solid. This is my reducing agent. The net reaction here is this. We have copper 2+, actually, let's go, Zn solid being oxidized by copper 2+ to form Zn2+ plus copper solid. And so my reducing agent is solid zinc. My oxidizing agent is copper 2+. Now I can't just have copper 2+, I gotta have some ions, anions in there. Otherwise I have space charge and I have an electrical neutrality balance problem. And so we'll throw in some nitrates in there. The nitrates are irrelevant because those are just spectators to maintain the charge balance, right? In the left beaker, do I need anything? In the left beaker, all I need is my reducing agent. But take a look at what they have here. Why do they have this? Look what they put in that beaker. In the left beaker, they're putting 1.00 molar Zn2+. Is that necessary? If I put in Zn2+, 1.0 molar, what is that? If I look at Zn2+, hey, wait a minute. That's not reactant. The reactant is solid zinc. This 1.0 molar Zn2+ is product. Hey, aren't we trying to make Zn2+? Are we trying to make Zn2+ in copper metal? Yes, we are. So if you're trying to make it, why are you dumping it in there? You know? This is like, oh, you know, I'm going to make some gold. Well, here, give me some gold, I'll dump it in there, and I just made some gold. Does that make any sense? No, it doesn't. So why are they putting this in here? It makes no sense. This is product. It makes no sense, but the product is required to maintain standard conditions. Do you remember standard conditions? Standard conditions, standard thermodynamic conditions are the solutions are at 1 molar, the gases are at 1 bar. And so if we're under standard conditions, that means all the aqueous solutions have to be 1 molar, whether it's reactant or product. This is really a dumb idea because you know what people use this for? People use this for batteries. Do you know what voltage we're going to generate in this battery? In this battery set up like this, we're going to generate 1.103 volts. If I got rid of this zinc here, this Zn2+, that is, Le Chatelier's principle says, you know, as the concentration of product builds up, the tendency is to shift left, right? So if I got rid of this 1 molar, do you know what's going to happen to that voltage? It's going to go up. You know, so it's kind of dumb. Why am I adding a whole bunch of product in here? It's going to ruin my voltage, and it's a waste because I don't need it. The reason I have it, though, is to maintain standard conditions. And the reason why I need to maintain standard conditions is because of Appendix D. All my data is under standard conditions. I didn't bring this point up in chapter 7 and 19. I should have, but I don't want to confuse it. Here, it's really apparent. You know, why are we putting product in there? It doesn't make sense. Well, it's because of this whole standard conditions business. But anyway, we're under standard conditions. We're going to get this voltage if we have this. Now let's talk about the construction of the cell. On the left beaker, we call this the anode. In fact, this piece of metal here, the zinc, is the anode itself. And this is called the anode part of the cell. At the anode part of the cell, oxidation occurs. So oxidation occurs at the anode, and the half reaction here is zinc solid goes to Zn2+ plus 2 electrons. Over here, this chunk of copper here is called the cathode. And at the cathode, reduction occurs. And the reduction reaction is copper 2+ plus 2 electrons yields copper solid. And the electrons flow left to right. As long as we have the anode on the left and the cathode on the right, then the electron should flow this way. Then we're going to have our salt bridge. In this case, it's potassium nitrate. The origin of anode comes from the salt bridge. That is, the nitrate ions are going to migrate to the anode compartment. That is, the anions in the salt bridge go to the anode compartment, and the cations in the salt bridge go to the cathode. So an for anions, cat for cations. Here. The salt bridge is called the internal circuit. The wire is called the external circuit. And so the electrons flow in the external circuit. In the internal circuit, the ions flow. If you look at the negative charge just makes a big circle. The electrons on the external circuit, the nitrate ions in the internal circuit. And so we just see this migration. The anode and cathode are examples of electrodes, and the electrodes have 2 jobs typically. One job is to be an electrical conductor. They have to be an electrical conductor to feed or remove electrons. And sometimes they're a reactant too. But not always. We can see that here. If I look at the anode is actually a reactant and electrical conductor. So as the zinc gets oxidized, it generates 2 electrons. The 2 electrons get fed into the zinc, which gets fed into the copper, which gets fed over to the cathode. Over here, the cathode, copper doesn't play a role here in the reaction. Copper is just a product. And so what the copper does is it feeds the electrons to the oxidizing agent, copper 2. So in this case, copper is not a reactant, but it's an electrical conductor that feeds the electrons. The electrons come in here, 2 electrons come in here. When 2 electrons come in here, they combine with copper 2 and they deposit copper solid. Over here, the actual electrode gets corroded. So zinc gets corroded to Zn2+, in the process generating 2 electrons that get fed into the external circuit. So in the anode compartment, we have oxidation. Cathode compartment, we have reduction. The anode and cathode are called electrodes. The electrodes are marked with a sign. So, for example, the cathode is feeding electrons to the oxidizer. Are oxidizers electron poor or electron rich? Electron poor. And so the cathodes are given the positive symbol. They're electron poor. The electrons are going to be fed to this electrode. Anodes are where reduction occurs. Anode is where we're generating the electrons. We're generating electrons, so the anode is electron rich. Anodes are given the negative symbol here. And so we generate electrons at the anode, which gets fed into the cathode here. And so electrons travel from anode to cathode. The symbol for voltage is V or E, or EMF. EMF stands for electromotive force, EMF. And E or EMF is the symbol. Cell, this whole thing is called an electrochemical cell, of which there are two types of electrochemical cells. There are electrochemical cells that generate electricity, in other words, electron flow. These are called voltaic or galvanic cells. And then there's another type of electrochemical cell in which you connect an electrical power source. So if we took this cell, connected an electrical power source here, we could force the electrons to go backwards. If we force the electrons to go backwards, we're forcing the non-spontaneous reaction to occur. And that would be called recharging this. This would be a battery. We would be recharging the battery. Like this. This is a battery because we have electrical energy stored in it. So this is a pretty involved drawing. We could do this as shorthand. The shorthand representation of that drawing is called a cell diagram. And this just shows the components of the cell in a symbolic way. The anode, again, is where oxidation occurs. And the anode is usually written on the left because we want electrons flowing left to right. The cathode is usually written on the right. In cell diagrams, it's always that way. And so let's take a look at a cell diagram. But there are two more symbols you need to know. A single vertical line shows a phase change or boundary between phases. If we see a double line like this, this indicates the salt bridge here. And so the cell that we just drew here can be represented by this. This is called the cell diagram. This is just this drawing or schematic of the cell. In the cell diagram, we have the anode on the left and the cathode on the right. At the anode, we have oxidation occur. So zinc goes to Zn2+. It generates electrons. Those electrons flow from the anode all the way to the cathode. At the cathode, those electrons are fed into the copper, which feeds them to the oxidizing agent, copper 2+. So copper 2+ picks up those electrons to generate copper metal. So we have reactant product at the anode. We have reactant product at the cathode. The double line here represents the salt bridge, which the cell wouldn't be able to operate without the salt bridge here. And so this is a shorthand way of representing this whole drawing here. Okay, the two types of cells, again, there's cells that produce electricity. Those are galvanic or voltaic cells or batteries, is one other word. And so batteries produce electricity by using chemical potential energy and converting it into electrical energy. The other type of cell we call an electrolytic cell. In electrolytic cells, we have non-spontaneous reactions that are driven by a power source. So we force electricity. In this case, we put a power source here and force the electrons to go right to left rather than the natural direction, left to right here. That would be an electrolytic cell. Electrolytic cells are used to recharge the battery or They're used to generate high energy chemicals like sodium metal, chlorine gas. So most of the sodium metal, in fact, all the sodium metal that people use in labs is not mined out of the ground. It's manufactured from sodium ion, sodium salts. Okay, we have some other things. So these are the two types of cells, electrochemical cells. And then we have some more shorthand here. This is called a couple. And we saw the couple in the cell diagram, and it's a pair of species. Would this be an oxidation couple or reduction couple? This would be an oxidation couple because we start with M and we end up with Mn plus. So we're losing electrons. That's oxidation. Oxidation is loss. That would be shown over here on the left. The oxidation couple over here is Zn. Zn solid goes to Zn2 plus. This vertical line represents a phase difference. This is solid, this is aqueous. So that's why we have the vertical line. If they're the same phase, we use a comma to separate them, reactant from product. And so this is going to be an oxidation couple. The reduction couple would be copper 2 plus goes to copper solid. One thing about couples is they aren't necessarily balanced. So for example, we might have an oxidation couple, which is hydrogen gas goes to H plus. Well, an H2 goes to 2 H pluses. But when we look at couples like this, we don't care about the stoichiometry, 2-to-1 ratio. What we care about is the concentration. Under standard conditions, all the concentrations are 1 molar, but under non-standard conditions, we could change that. So if we put a 2 here, does that mean it has to be 2 molar? No, a 2 just means it's a 2-to-1 ratio, mole to mole here. And so this has nothing to do with concentration. What we're interested in is the concentration. Now the concentration is going to have an impact on this. Because under standard conditions, this is what this cell looks like. Let me go back. Under standard conditions, we can think of this cell as being a tug-of-war. So over here, we have Zn2 plus, 1 molar. Over here, we have copper 2 plus, 1 molar. Zn2 plus is an oxidizing agent, copper 2 plus is an oxidizing agent. Both are pulling for electrons. So you have 1 molar Zn2 plus, 1 molar copper 2 plus. They're both pulling for electrons. Which one's going to win? The copper 2 plus is going to win because copper 2 plus is a stronger oxidizer, right? Well, what if you did this? What if we said, okay, rather than 1 molar, let's go 6 molar. If I did 6 molar copper 2 plus, what's going to happen in the tug-of-war? Well, what do you think is going to happen to that voltage? If I went from 1 molar now to 6 molar, do you think that voltage is going to stay the same or change? It's going to change. Is it going to increase or decrease? Well, if I have 6 molar, 6 times as many copper 2s now, is it going to pull with more force or with less force? Let's say you have a tug-of-war. The other team just went from 1 person to 6 people. Is the other team going to pull with more force now or less force? So now you're zinc. You've already been overpowered by copper 2. Zinc 2 plus is fighting a losing battle because copper 2 is stronger, right? And now all of a sudden copper 2 is 6 times as many ions. What's going to happen to that voltage? It's going to go up. And so what we care about, well, what if we did this? What if we went from 1 molar, we went down to 0.01 molar? What do you think is going to happen now? The voltage is going to go down because we don't have much copper. So this is like, okay, now let's say you have 10 versus 10, and all of a sudden 9 people left on the more powerful side, then maybe the weak side has a chance, right? And so we care about the concentration because the concentration is going to make a difference in the voltage, how much pulling power there is. And so this is why, like in these couples, we don't care about that, the stoichiometric coefficient, we care about the concentration. Here. All right, so let's, that was the first section. Let's take a break and then we'll continue with section 2 here next.